let's have a look at this ATX power supply, just for the fun of it, yeah, just for the entertainment and educational value of it. So I've connected it to the current limiter, the light bulb. I mean, when I tried this in the PC, it didn't draw any power at all, so nothing was happening. I can probably move the camera so you can see the current limiter. Yeah, oh, that's, yeah, it's there. Sitting on top of the variac, there's a light bulb. Great. A bit more, yeah, nicely in shot now. So that's the current limiting light bulb. It's set to limit. So when I plug this in and switch this on, you would normally expect to see like it flash just to say power's gone into it. Now, if this has active PFC circuit, quite often it'll just continually flash bright. That's quite normal. If it has a short inside, it will just come on, but that didn't happen before. If it's drawing no power at all, it won't light up. So I've connected the power. Let's switch it on and let's see what it does. So it does nothing. So we can say that it's not drawing any power. I don't think the main capacitors inside have charged up, because otherwise the light would flash if any current went into this. So this seems to be completely dead, no current coming in whatsoever. There's no fuse here in the socket, so we'll have to open this up and have a look to see what's happening with it. This, by the way, is my modified ATX power supply tester analyzer. I originally reviewed this, and then having used it for a while, saying it was quite handy indication for working on power supplies, I found it had a major problem, which is that if the 12-volt supply from the ATX isn't present, even if all the other voltages are present, it doesn't light up, it's dead, it does nothing. So I modified this to work no matter which voltage rail is present, whether it's just standby, even if it's just 3.3 volts, this will come on and give you a reading and show you that there's some power coming in from somewhere. So that's the test that we have, and that's obviously not doing anything either, which is another indication there's no supply coming out of this power supply. Now it is time to open it up. So they're quite easy ATX power supplies. There's a few things you need to bear in mind when you're working on these. There can be high voltages present inside. I mean, when it's connected to the mains, obviously there is high voltage coming in. They have a large capacitor, or two large capacitors on the power input that can store, in some cases, power supplies with active PFC can have almost 400 volts in there, and they can store that voltage for quite a long time. So they can be dangerous if you don't understand them or know how to work on them safely. The capacitors I mentioned are these two here. This has two heat sinks. This one will be all the diodes on the output, so this is the low voltage side, and three transformers. So effectively everything this side of the transformers is low voltage with a safety ground, and it's safe, apart from the fact they put the mains connector over here, which actually is not good. All the main circuitry should be isolated to one side and the low voltage to the other. It certainly is on the PCB. So this side, which is this heatsink, which has, I can see, three devices on, is the high voltage side. This is the dangerous side. If it had active PFC, it would almost certainly have a third heatsink nearer to the edge, or sometimes I've seen them sideways. I mean, it could be mounted anywhere in this area, but it could have three. If you see three, it has active PFC, which basically boosts the DC voltage coming in to about 380, 390 volts before the power supply runs and drives the transformers to generate the outputs. So ours basically appears to have no power whatsoever. The first thing I can see here is a fuse. So we'll have a look at the fuse, but we'll also just check that there's no charge in these capacitors before we actually do anything else. I'll get the voltmeter and let's have a look. I have the voltmeter on the auto range. With a power supply like this without active PFC, you can check if there's any voltage in the capacitors by reading across the bridge rectifier. That's this device. So we can just go from the plus and minus outputs of this, and that's just actually telling me there's a short there. Oh, that's clever, this meter, isn't it? It's the first time I've used this on a live repair, and it's told me straight away, first of all, there's 0 volts, and secondly, we have a short. So we have a short on this. If you don't know if it has active PFC or not, then this isn't a safe way to test if there's any charge in the capacitors. I'll just actually show you on a piece of paper why that is the case, because this is actually quite important. With an ATX power supply like this one, and many switch mode power supplies, you will have coming in from your AC, live and neutral, to a bridge rectifier, which is basically made up of 4 diodes. But I'll just draw it as a box with 2 AC inputs, plus and minus, coming out. And from the plus and minus will go to your large capacitor or capacitors, which are here. Right? And then this drives the actual switching transistors for the power supply. So what you have is, when you power this up, this capacitor charges up. And it'll charge up on a power supply like this to about 270 volts, something like that, on a 220 volt supply. That's the peak voltage. And if there's nothing running, there's no load, there's an open circuit fuse between here and the load, or for some reason the main switching transistor is just not running, when you unplug it, this capacitor will still keep a charge. And because there's nothing to discharge it, you can hold that voltage for quite a long time. I mean, we can talk in 30 minutes, possibly. And that's why they can be dangerous, because you've unplugged it from the mains and you haven't appreciated the fact this capacitor has a high voltage in. And on this type of supply, which actually has 2 capacitors in series, I'll explain this whole thing to you in a minute. But with this type of supply, if you measure with your test meter between the plus and minus on the bridge rectifier, so we go to your test meter, I'll draw an analog one, and you measure here and here, you will see if there's any charge in the capacitor. So you can quickly tell, before you remove this PCB to get underneath to where the capacitor terminals are, you can see if we have a charge, a high voltage, a dangerous situation. And that's what I did with this. Now, we also get other, particularly ATX power supplies, that are connected like this. So you have live and neutral coming in the same. We have a bridge rectifier, AC, coming out the same thing, plus and minus, okay? And this then goes to a circuit called a power factor correction, or PFC. So basically, this goes to an inductor coil, like so, and from the inductor coil, we have a MOSFET going to ground, sometimes through a low value resistor here, possibly current sensing. And this MOSFET is switching on and off very rapidly from the PFC controller, very high frequency. And it effectively rapidly charges and discharges the magnetic field in this coil. Coming from here now, we have a diode, and here is the large capacitor, or capacitors. Okay? This is a boost controller, PFC. This is a boost controller. Sometimes as well, there's another diode from here across to there, okay, as well. Sometimes you find that. Now, what happens here is this boost controller increases the voltage in the capacitor. So this voltage on the capacitor is about 380 volts, okay, or you may have 2 in series, 190 in each. When you now switch it on, say the PFC is running, or even if it isn't running, DC will flow through here and you'll end up with 270 volts here rather than 380. But whether or not this is running, you'll end up with a high voltage here. When you then unplug the mains, if the power supply isn't running, there's nothing to discharge this capacitor, this will keep its high voltage, and it could be 380 volts. If you then measure here, what we just did before, so we come across it with our multimeter, okay, and we measure the voltage here, we won't see any voltage, and the reason is because these diodes are now reverse biased. The current can't flow this way, so this can still have a dangerous voltage, and you would read 0 here. That's why you need to know when you're checking for the charge in the capacitor which type of circuit you have. If you know it's a PFC, you can easily spot this diode and normally measure from here to here. But otherwise, the only safe way is to remove the circuit board carefully, or wait a good while for the capacitor to discharge, and then measure across the capacitor itself to see if it's safe to work on. So what should you do if you find there's high voltage in the large capacitors and you want to work on the item? To do that safely, you need to discharge the capacitors. You could use your voltmeter periodically to check to see what voltage is there, and it will gradually go away. Could take some time depending on the value and the quality of the capacitors. In some circuits there's actually a high value resistor wired across there, so it will discharge anyway after a period of time. The other way is to discharge the capacitors. Now, the way you should definitely not do this is to use a screwdriver and literally short the capacitor or capacitors, or even in this case, because they're both in series, just short the two right across the two. This will cause a flash and a bit of a spark, or quite a lot of a spark, which is actually quite hazardous. So I mean, you could end up with a situation where the spark, which is literally sort of vaporized or incandescent metal fragments going into your eyes, which you don't want. It's also very bad for your tools to do that as well. I had a situation not so long ago where I had a circuit board fall over onto a screwdriver, and the capacitors were charged. It wasn't plugged into the mains, and it actually damaged the screwdriver. So using that method, and the same method by the way, pair of long nose pliers to short it out. Yeah, this is dangerous in two ways by the way. One is that you have the same hazard of flying sparks, and the other is that it's quite easy to effectively touch this part of the pliers and find that you actually discharge it with your fingers rather than with the pliers, which is not what you really intended to do. So that's not a good idea. The last reason why you shouldn't just short out the capacitor is that it's very, very bad for the dielectric, the insulated layer inside the capacitor, because all that current that's flowing at that time when you short it out is very, very high, if only for an instant, puts a huge stress on the dielectric inside the capacitor. And you'll get away with it probably quite a few times, but sooner or later you'll actually damage a capacitor or destroy a capacitor by using that method. So how do we do it safely? Well, the answer is to use a power resistor like this one. The value is not critical. This is a 3.3K. You could use a 2.7, 4.7, something in this region. The higher the value, the longer it will actually take to discharge the capacitors. This is I think it's a 5 watt resistor, and I can use this just touch across the capacitor terminals and very quickly really discharge the capacitor. It would probably take, if you hold it there for 5 seconds, it's discharged. Once again, you can check with your voltage meter to make sure it is fully discharged. So that's how you should do it, using the power resistor, something like this, which I salvaged. It's probably a good idea actually to attach this onto something insulated, but make sure it's firmly attached, maybe like a lollipop stick type thing, and then you can actually hold it at a little bit of a distance if you're worried about getting your fingers too close to the circuit board. So that's how you should actually discharge the capacitors. Once you discharge, you'll find it safe to work on. Another common hazard with repairing and working on power supplies like this is regarding the on-off switch. So if you look down here, you'll see you have a single pole on-off switch, which has 2 terminals, and the switch on the back literally makes or breaks the contact between the 2 terminals. Now supposedly this switch will be in the live wire, so that when you switch it off, you're disconnecting live, but the neutral is still attached, which is safer than switching the neutral wire. I wouldn't say it's totally safe, but it's safer. Yeah. But what you need to consider is, I'm in the EU and maybe where you are, do you have polarized mains sockets so that you always know which is live and which is neutral? You can only put the plug into the mains in the wall one way round. And if you do, are you certain that the electrician who wired up that building wired that socket the right way round, the live and neutral, because it'll work the other way round from an electrical point of view. It's just AC. But do you want to rely on that for your safety, that when you switch this switch, you're actually breaking the live wire? And lastly, do you trust the factory, the company who made this, often very low cost devices, that they wired the switch in the correct lead between the live and not between the neutral? Do you really want to trust your life, you know, which it could be? Do you want to trust your life with the fact that whoever wired it up actually wired the switch the right way around in the first place? So the upshot of all of this is the only way to know that this is isolated from the mains is to unplug the lead. Just always remember that, and that will keep you pretty safe. Regards the power supply design itself, there are probably quite a number of designs or topologies, which is the posh word for design, of power supplies. But with the ATX power supplies, I've generally come across three sorts. Okay, so this is typical of an ATX power supply design, and with this particular topology you can identify it by the fact it has three transformers. Now you may well think that the reason it has three transformers is because it's got 3.3 volts, 5 volts and 12 volts output, so that's one transformer for each voltage rail. Yeah, well actually no, that's not what they're doing. All the voltages are being generated by the large one of the transformers. When I say all the voltages, I mean all the main voltages, the 12, the 3.3 and the 5. The other two transformers, one of them is for the standby power supply. So this will be, in this case it'll be this one, and I can tell you why I know, because it's nearest to the transistor there which is driving it. And I can also tell by the components that are surrounding it as well, actually, these capacitors. You got a torch for you. Those green capacitors down there, yeah. This is the standby supply. This generates actually 2 voltages, I'll show you in a minute. But the main idea of this power supply is when you switch on, the standby comes on and it powers up this chip here. On some designs you'll find one chip like this, and some you'll find 2 chips. Okay. If there's the one chip, then what it's actually doing is 2 things. First of all, it drives the main power supply, and secondly, it monitors the various voltage levels and current levels. The other common thing you'll find is 2 chips. One is driving the main power supply, and the other one is monitoring the current levels and the voltage, so they're in separate chips. So in this case, we know that from this design, this will be powered by the standby. It waits until it gets an on signal. So the purple wire, this is your standby voltage coming out to the ATX plug. And on the ATX plug, the purple wire supplies 5 volts into the motherboard for the standby circuitry. And when you press the start button, it connects the green wire to ground. And that green wire comes back. In fact, you can see it, it's coming down here again near to this chip. This puts 0 volts onto one of the pins on this chip, or sometimes 2 pins together, and this chip then starts running. Once this chip starts running, it actually drives some little transistors. They're usually somewhere down here. They could be here and here on this one. These little black things with like a, yeah, you see the 2 of them there. The second one's kind of like, yeah, my torch is too bright, but it's there under the spotlight now. So this chip, or the one of the 2 chips, will drive these transistors, which will drive the middle transformer, and this middle transformer then drives your main switching transistors, which are over here on the big heatsink. Okay, so this transformer basically isolates the low voltage side from the high voltage side, the same as the one driving the outputs, and the same as the one on the standby. Anyway, once these start switching, this will then drive the main transformer, and that'll give you your main outputs. The last thing you can notice, particularly the 3 devices on here, these are rectifier diodes, what are called Schottky diodes, very fast acting diodes, and these are for your voltage rail. So one of these will be the 12 volt, one will be the 5 volt, and one will be the 3.3 volt normally. So that's basically how your power supply works of this design. But I know if I show you that on a piece of paper, it'll be a lot clearer. So let's look at this one, and then let's talk about a few of the variations that we find. One other thing I'll just mention before I draw this is we see down here a little black component with 4 legs. You can see right by the transformer. That's an opto-isolator. In this circuit, the opto-isolator will be monitoring the output of the 5 volt standby. So when it gets to 5 volts, it will then compare that output, the 5 volts, with a reference, which is in one of these 3 devices. What 2 of them are the transistors, and one is a reference chip called TL431 normally, and that is a reference voltage. So it uses that reference to know whether the purple wire, the 5 volt standby, has the correct voltage on, and it signals back through to this circuit via the opto-isolator to say I need more or less voltage. So that's what that does. Now we've explained pretty much all the components. Let's have a look at this topology on paper. We know then we have mains power coming in. This can be with or without PFC, so I'll just do both of them if you like. So we have the mains coming in to a bridge rectifier, AC, AC, plus, minus. On the input side, there's usually a few inductor coils just to stop interference, and capacitors. There's often a fuse, and this thing a PTC, an NTC, negative temperature coefficient, a thermistor to stop inrush current. So that's what that lot does. This is your bridge rectifier, this one here. So from your bridge rectifier, you've either got a direct connection to the main smoothing capacitors, or you've got PFC. The PFC, there's 2 ways you'll find this. Sometimes there's just a big inductor coil from here going to the capacitors. In this case, I'll draw both the capacitors because there are 2. Okay. Sometimes you find that this coil will be big and heavy, and it's normally bolted to the lid that fits on here with just a couple of wires going to the board. So if you see that big heavy, it looks rather like a transformer, but it's or a choke you might call it. That's what it is. Sometimes you'll find that, and that is what is known as passive PFC. If you find this type of circuit, by the way, you can safely measure the voltage at the bridge rectifier to see if it's charging the capacitors. The other one, which we've just discussed, has the diode in here, has the MOSFET, usually a low value resistor to ground, and the PFC controller. PFC, power factor correction. And as I say, sometimes a diode like that as well. Okay, that's the second type. The third type, and common like this, is it doesn't have this, it just literally has a connection from here to here. And that's what we have. Now, why do we have 2 capacitors in series? Is it because the PFC can generate 400 volts, so we can use 2 200 volt capacitors rather than 1 400 because they're easier or cheaper to find? No, that's not actually why we have it. This circuit in these type of power supplies is called a half bridge. So the half bridge basically has 2 MOSFETs in series across the main supply, plus to minus, with or without PFC. These MOSFETs are switching your main transformer, the one that's generating your main output voltages, and they're connected, not directly, there's normally a couple of diodes and capacitors involved, but they're connected to the transformer you see in the middle, the driver transformer. So in this case, this is the primary, the input, and this is the secondary, the output, whereas the other 2 are the opposite way around, primary, secondary, primary, secondary. This transformer is actually driven then usually by a couple of transistors, which are, as I say, 2 two of these three that we can see. And these transistors, I'll just sort of draw them, that are driving these, normally go to a voltage supply. In fact, they would go to a voltage supply. Again, there's a little bit more circuitry involved. And the two transistors are controlled by the pulse width modulator. Pulse width modulator. That's this this chip down here, which may be one or two chips, depending if the monitoring is part of the chip or it's separate. So that's what we have. Your transformer, the main prime of your big transformer, your output transformer, is actually connected from here to here, but it doesn't actually go directly. I'll show you the capacitor. The transformer's here, okay, and it connects via a high voltage capacitor, the junction of these two capacitors. This is your transformer, and on here you have 3 windings usually, and these are going to your actual outputs. Okay, your 3.3, your 5, your 12. One end of the transformers are all basically connected to ground, and in here we have the rectifier diodes. Okay, one for each. Okay, and this is generating your, in what order, 3.3 volts, 5 volts, 12 volts. And then on these outputs, obviously you're going to have capacitors, okay, to ground on all of them, and sometimes more than one capacitor. Okay, that's basically how it works. You then have either part of this chip or a separate chip, okay, which is effectively monitoring all of these various voltage rails with resistors, networks of resistors, and that is effectively the monitor, the voltage monitor, current and voltage, and that controls the pulse width modulator to affect the drive going into here. So that's how the main supply works. But for this to work, this needs to be able to run. This needs to be able to start to drive these, and to do that it needs a power supply. Okay, so what we then have is this. This is your standby supply. So again, coming from the main input voltages, yeah, you will go into your standby supply. I've drawn it upside down, so I have to draw it like this. This will have a coil in it. It'll have usually a MOSFET or a transistor, and this is your standby STB. So I have a little controller, a little power supply with a MOSFET or a transistor driving another coil, and this generates your 5 volt standby. Okay, once again, diode, capacitors to ground, and that's your 5 volt standby. Okay, that's what the standby supply does. So when you power up, this circuit starts running straight away, generating 5 volt standby. 5 volt standby, as I said, goes to the motherboard, which allows the motherboard to send a signal back here, PS on. This is your green wire. This is your 5 volt standby going out. This is your violet wire or purple. Yeah, and that's how it starts. Now, you remember I mentioned that these transistors switching the main drive through the transformer need a power supply. Well, usually 5 volts isn't enough for that. So what you usually find is, as well as having a secondary for the 5 volts, you'll have another secondary on here. Okay. Another diode. Another capacitor to ground. And this voltage, we'll just call it X, goes to here. And that's usually about 16 volts to about 24 volts. Could be 12 volts, but it's somewhere in that region. Yeah, driving these transistors, this circuit. So that basically is how the whole power supply works. Take a photo of it and stick it on your wall if you like. But that is basically a bit of a dicky cad. Okay. 2022. Okay. That's the way it works. There's one other thing I mentioned when I was showing you around it, and that's the opto isolator. So the opto isolator basically monitors the voltage on the 5-volt standby. And the opto isolator, which is here, so this is an LED. Okay, LED going to ground, and effectively it monitors the voltage here. Okay, when there's enough voltage, the LED lights up, and inside here is a transistor going to hot ground, not the same as ground. And this transistor basically controls that standby supply effectively, so it maintains the 5-volt. Now let's talk about ground, shall we? You have isolation on this. Let me show you on the circuit board as well, because this is also important. Okay, I've taken the circuit board out. This is the high voltage side of the power supply. So your mains comes in here, fuse, filters, bridge rectifier, capacitors, switching transistors, and we've just discussed how it works. So if you look underneath, you'll see there's like a big gap here, yeah, where there's no circuit traces. And this divides the high voltage side from the low voltage side. So on the low voltage side, there's absolutely no electrical connection from there to this side. The only connections are through the 3 transformers, primary to secondary, primary to secondary, they drive the opposite way, primary to secondary. So that's your 3 transformers, here, here, and here. And then the opto isolator, which is here, which has an LED on one side and a photo transistor on the other side. There's no electrical connection. On this side, ground, 0 volts, is ground. That's connected to the safety ground of your PC case, the ATX case, and there's no connection from that ground to anything on the high voltage side. On this side, ground is actually the negative end of the bridge rectifier and one of the capacitors. So the bridge rectifier negative is ground on this side, but that is not safety ground at all. For instance, you cannot connect anything grounded to this, not even an oscilloscope probe, without causing some damage. And I'll just explain to you why that is and what the difference is between hot ground, as it's called over here, and safety ground, which is all over here. To understand the difference between safety ground and hot ground, we need to just understand how a bridge rectifier works. So a bridge rectifier is actually made up of 4 diodes, and they're wired up like this. So we have 2 diodes wired like that, and then we have 2 more diodes wired like so. There, okay, and that is a bridge rectifier. This here and this one, this is AC, live neutral or live neutral, whichever way you've got it wired up. That's AC, and that's your AC supply coming in. This is your positive, and this is your negative. Okay, negative, positive. And across here we have 1 or 2 large capacitors, so we get smoothed DC. Now, the way this circuit works, and the reason of the problem with hot ground, your AC signal is going positive and negative, okay? So on the positive half cycle, when this end is positive with respect to this end, the circuit path is basically in here. So this is now plus and this is minus, yeah, on the half cycle. So now this diode will conduct positive to negative. So the electric current runs in through here, okay? Can't go down there because the diode's reverse biased. It can't go down there because it's reverse biased. Through here into your capacitor, and this is your load. Okay? So it runs into here through the load, back to here. This is forward biased. This is negative. This is the negative end of this diode. This is the positive end. So it goes through this diode, down here, and back to negative. So your path is through there, through the load, up here, through here, and to here. You can't go back through this one, by the way, because this is positive. This is more positive than this end of the load, so it's reverse biased, yeah? It can't go that way. The diode's reverse biased. This end is more positive. So that's what happens. On the next half cycle, this end now becomes negative, and this end becomes positive with respect to the other end. So now what happens is, the current flows in through here, this way, positive to negative, and now it goes up through this diode, okay? When it gets to here, it can't come back down here because it's reverse biased. Let me use a different coloured pen, make it clearer. Different coloured pen. So from positive, through the diode, through the load. Notice it's going through the load in the same direction, plus to minus. So on both half cycles, it still goes through the load in the same direction. This is DC. Okay. Back up to here. And when it gets to here, it needs to go to negative. And if you look, this diode now is reverse biased because this is negative and this end is more positive than this end. So the current flows through there. And there's your complete circuit from plus to minus when this end's plus. Yeah? And your complete circuit the other way when this end is plus and this end is minus. Okay? That's how your bridge rectifier works. Right, where do we connect the ground? Well, we connect the ground here. This is our reference point for the test meter, the negative end of the bridge rectifier, the negative end of the capacitor. That's your ground. But is it safety ground? No, because it's connected to the mains. On one half cycle, this is connected to the live or neutral, depending on which half cycle it is. But on one half cycle, this point is connected to here via one of the diodes. Yeah, and then the other half cycle is connected to the other one. Okay, so effectively, whichever end is the negative end of the half cycle with relation to the other, that's where it's connected. But half the time, it's connecting to here, and half the time it's connecting to here, and that's why it's not a safety ground. It's only a reference for measuring voltage in this circuit. Do not connect anything grounded to here, whether it's an oscilloscope, whether it's a USB device, electronic device, anything like that. Don't connect it to here because you'll damage the device you're attaching, you'll damage the device you're testing, and to be quite honest, if you connect yourself to here, you might damage yourself as well. So do not touch hot ground. It's a reference point, it's not a ground. Now the other side of the power supply, the low voltage side, is all driven via transformers. So we have the main power transformer with the 3 outputs, 12 volts, 5 volts, 3.3 volts. We have the standby transformer with its 2 secondaries, 5 volt standby, and that other voltage that drove those transistors, about 16 volt. We'll call it standby, yeah. And we have an opto isolator, an LED, shining on a photo transistor. Okay. This is your hot ground. Yeah. At the bottom of this transformer coil, this is your hot ground. Bottom of this one, this is your hot ground. Yeah, they're all hot ground. The one we just discussed. Okay. And this is your output of here. But there's no connection between the two sides. There's no physical electrical connection between the two, because this uses galvanic isolation, it's called, it's actually a magnetic field, and this uses opto isolation, light. So on this side of your power supply, all these are connected to safety ground. Okay. The black wires in your ATX power supply go to the motherboard. This ground. Okay. Now this ground is isolated from this ground by this. So they're not the same thing. Hot ground is perfectly safe to put your black lead of your meter, or even the red lead of your meter, on if you so wish, and measure voltages on the high voltage side with reference to there. That's how we test these circuits, but it's not safe for your finger or anything that's grounded to attach to it. This ground is in no way connected to the mains, so it is perfectly safe, and you can connect any grounded equipment to the ground on here, and you will not cause any problems either to the equipment, the power supply, or to yourself. This circuit, by the way, is called a half bridge, and quite often these are not MOSFETs, they're actually bipolar transistors connecting collector emitter like so. Okay, so quite often they're actually bipolar transistors in here. And just tell you basically how this works. So it's designed such that only one transistor turns on at a time. So when this transistor turns on, the current flows from the positive here through the coil, through this capacitor, at least while there's a change. This is AC current, yeah, so AC will pass through the capacitor, and effectively charges this capacitor. So current's passing to negative while it's charging. So that's the way the current actually flows when this transistor switches on. And obviously it's designed in such a way that this transistor doesn't stay on long enough to fully magnetize the coil or to fully charge the capacitor. So that's the way that actually goes. Then this transistor turns on. So this turns off and this turns on. And what happens actually now is the current actually comes the opposite way. So effectively it's coming down through this capacitor, through the coil in the opposite direction, down through this transistor to ground, hot ground, yeah. So depending which transistor is switched on, the current is flowing backwards and forwards through the transformer, and that gives you an AC signal that drives the secondaries. So that's how actually a half bridge circuit works. Common things that go wrong, by the way, with this. Let's just look at the common things that will fail. So short circuits in the transistors, or open circuits, this will stop working. If there's a short circuit here, almost certainly blow the fuse. It may blow other things like the bridge rectifier. Fuse is basically here. This is where your fuse is. Okay, so that is a common failure. Another common failure is that the standby supply doesn't run. There's no standby, therefore there's no 5-volt standby, so it can never switch on. That's a common failure. Another common failure is that the pulse-width modulator chip isn't running, so it can't drive the main supply, so you get standby but nothing else. You can have problems in all this monitoring whereby you have unstable voltage outputs, or you have a situation where it shuts down because it thinks there's an overvoltage and there isn't. So that's fairly common. And another one that is quite common is this capacitor fails, the one that's generating this voltage, about 16 volts, that powers this part of the circuit. So although the thing starts up and this is running, it can't drive the transformer to drive the base of these transistors because there's no supply here. That's quite common. But to be quite honest, and another one, these rectifier diodes go short circuit. If one of these goes short circuit, it puts a big load on it, or sometimes blow the main fuse, or it just won't run, or it just won't, you'll get standby but it won't switch on. There's a number of possible symptoms, but that's another one. I mean, to be honest with you guys, you know, there's lots of things that can go wrong in here, but those are probably the most common problems I've seen. If it's got PFC, then the PFC controller sometimes fails, or this goes short circuit. Again, will blow the fuse normally. So that's what usually goes wrong with this. So let's have a look now to a couple of the variations on this that you're commonly going to find. I mean, I doubt I can tell you about the design of every ATX power supply out there, but I think I can tell you at least 4 of the main ones. So let's have a look at another typical design that you'll come across quite often. A very quick recap, the one we just looked at. 2 main capacitors, 2 sets of heat sinks, 3 transformers, and then the main pulse width modulator, current voltage monitor chip is here on the low voltage side. So the main way to spot this is the 3 transformers. That's the obvious thing, and the 2 capacitors for the half bridge circuit. The other common type of power supply is this one. With this type of power supply, there are some very obvious differences. We have straight away 2 transformers, okay? 1 large capacitor instead of 2, 3 large heat sinks. In fact, there's a smaller one, but that's actually just bolted to the bridge rectifier. And we also have 1, 2, 3 opto-isolators. And if you look down here, there's another little circuit board down here as well, and I think you can probably see the legs there. There's another IC mounted on here. So how does this supply work? What's the difference? Well, I'll tell you straight away a few things. This is your PFC. This is active PFC. This is actually a faulty one. Some components been removed. It's one I have been working on and may well go back to working on. But this is where your PFC normally goes down here. So you'll have your MOSFET and you'll have the diode I was just explaining to you, the PFC circuit. I'll show you on paper again. You'll see it's what's there. On here, you have one device and then another one here. So on this, there's actually 2 devices. Okay. One of them is the standby supply. We need a standby supply. The other one is driving the main transformer, the one that's generating the 3.3, the 5, and the 12. It's always the biggest transformer. That's the way to spot it. On here we have some diodes. So these will be your rectifier diodes for your 3.3, your 5, your 12. This probably has 2 12-volt supply rails. You know, one going to the main board and then ones that go to the various plugs as well. And here we have a chip. This chip is actually the current and voltage monitor. And this chip under here is the one that's driving the transistor or MOSFET for the main supply. And it's also driving the PFC. So the first thing you should realise with this design is the controller for the main switching transistors for the PFC is on the high voltage side. Yeah, not on the low voltage side, it's on this side. This is why it doesn't have 3 transformers, it only has 2. Okay, it's also why it has 3 opto-isolators. Look underneath, the same things. You have a big divide down here. Okay, high voltage side, low voltage side. Now let me show you diagrammatically on paper how this works, and then you'll be able to see the main differences between this one and the previous design we looked at. This type of design is usually used for higher powered power supplies, and if you like, more modern ones as well, but not the latest ones. So with this one we have live neutral coming in, bridge rectifier. So this is the same, plus minus, and then here you'll have your fuse, if there's a fuse fitted. This is the actual fuse here. These are filter coils, there's capacitor down here. So these capacitors, all this circuit is to stop mains interference basically. Your bridge rectifier is there on the heatsink. So we have that the same. These power supplies, I would say, always have active PFC. So you'll have the inductor coil, which we discussed earlier. You'll have the MOSFET going to ground, often with a low value resistor in it. So when I say ground, this is hot ground. You know that now. This is hot ground. Usually with a symbol like a solid black ball like that. That's usually a symbol for hot ground. This is controlled by your PFC controller, which we'll put down here. And then we have the diode in here. Okay. Quite often another diode here. And this is your boost controller. So out of here then, 1 large capacitor, not 2. and this is a 400 volt capacitor, and it normally has about 380 volts in it when the thing's actually running. So that effectively is your input circuitry. I'll just show you. They removed on this device, unfortunately, but this had there's had a MOSFET and a diode. So a while since I removed them, but they went down here. There's another diode on here as well. This inductor, by the way, this is this one, okay? And the diodes, you see, I think these two are the MOSFETs, and that is the diode. I can soon tell, yes, looking underneath it, this has 2 pins. So it's had 2 MOSFETs in parallel here, and it had 1 diode, which was the diode we see here. Okay, this one. So that's what it looks like physically. Now, from here, we have the MOSFETs for the main switching circuit, the actual power MOSFETs. On this board, actually, there are 2. I'll just explain that in a minute. I can see them. And the MOSFETs are here, this one, and here, this one. I assume they're MOSFETs. It could be bipolar transistors. I think they're MOSFETs. I'll show you where these MOSFETs are. I just actually lost a bit of the recording, so I'll just do this again for your benefit. So this is the main capacitor. We have the negative towards this terminal, so this is minus and plus. And from the positive, we have a connection going to the first MOSFET. I'm pretty sure they are MOSFETs, which is here. So this is almost certainly the drain. The source then goes to the coil, and the other side of the coil is here. And this then comes back to the drain of the other MOSFET, which is here. And then from the source, brings us back to the negative. So that's where our 2 MOSFETs are actually in the circuit. And I'll draw these again for your benefit, because I lost a bit of the recording. So we have 1 MOSFET here. We have a coil. We have another MOSFET here, and it goes to negative. So that's where our 2 MOSFETs actually are. And again, these will be driven by the controller, so we'll just bring these down here. Okay, and the gate of this one. I'm sure they don't go directly, there'll be a bit of circuitry in between, but this is the gist of it. So on our design, we have 1 controller chip. It's under here. It's a CM6800. I'll take the plastic off. Yeah, you can see the chip there now. So this controller chip is on the high voltage side, different to the previous design we looked at. And the controller chip is here. And this controls both the PFC and the power supply. So this is a PFC plus pulse width modulation controller. And that's what we actually have on our board. This is connected to ground, hot ground, the negative end of the bridge rectifier, so that's ground. And this requires a power supply to run. I'll come back to that in a minute. So that's the primary side of it. All this is on the main, the hot side of it. Coming off the transformer here, then we have the various outputs, all from this transformer. And this is your 5 volt, your 12 volt, and such like. These are your main outputs, okay? 3.3 volts. These will go through rectifier diodes, as before, and they'll have capacitors on them. Okay, and that will happen on all the voltage rails. So that's what we have there. Now, we also have a standby supply as well. On this one, the standby supply is actually a chip here. This thing, yeah, which you can see has 7 legs on it. That is powering this transformer. So we have, and I'll draw it on here, we have a standby, a 5 volt standby. And again, it might be generating a 16 volt, but I don't think so, because this doesn't have the third transformer on this side. It probably just has 5 volt standby. So this is powering another transformer. Going to hot ground again. So this is all on the high voltage side. And this is your output side. Okay. This is your safety ground. This is your 5 volt standby. Again, it'll have a rectifier diode. Just draw it, and it'll have a capacitor to ground. So we have that. Now, this then powers this chip. This is not a pulse width modulator because the pulse width modulator is already here on the high voltage side. This chip is basically a power supply monitor. This monitors the voltage on all the power rails, the current draw on the power rails, and it also handles the on-off signal. So like before, this goes to the violet wire, purple violet wire, okay, purple, whichever one you want to call it. And it also supplies our PSU supervisor, it's called. Sorry, my writing's a bit rubbish. Supervisor, okay. This then monitors the green wire coming in, the power supply on, PS on, okay. When it sees the PS on signal, it needs to turn on the main power supply, and it does it using the opto isolators, and we have 3 opto isolators. So I'll just draw them on our circuit where they actually are. So one of them is here, okay. A little transistor thing, and we'll put them where we need them. 2 of them are here, okay. Yeah, LED and the little photo transistor, okay. I'm drawing it slow because it gives you time to think about it. Right. What they do? Well, one of them is switching this on, okay. So these will go to safety ground. There'll be a bit more circuitry involved, but one of them is switching this on, and the way that one actually works is controlled by here. So this sends a signal out which turns this LED on. This end is normally connected, well, it will be connected to safety ground, and this switches this chip on. Now sometimes the chip will actually have an enable pin, so it puts an enable on to switch it on, and it's powered from the main supply. But I happen to know on our chip it doesn't work like that. It's actually, this goes to a voltage regulator which has an enable pin on it, and the voltage regulator effectively is powered from here. I think it actually comes from this side of the bridge rectifier. Yeah, it's powered from here via high value resistors, and this is your voltage. It's a 15 volt regulator, and this powers the chip. Quite often you will find that the power for this is not coming, as I showed you, from a high value resistor up here. You will find that on the standby transformer you'll have another secondary, but rather than being connected on this side, the low voltage side, the secondary is actually connected on this side. So the secondary again goes from hot ground. I'll draw it here because I can't fit it anywhere else, but it's just that although it's on what you might think the primary side of the transformer, it is actually a secondary winding, and this goes to the 15 volt regulator, and this is often sort of maybe 24 volts or 20 volts, 16 volts, somewhere in that region. This is why I mentioned earlier there probably would be another winding on here as well as the 5 volts. Obviously, just to be sure, there's a diode in here, and there's a capacitor to the hot ground as well. So you quite often find that's the actual layout of these types of power supplies. So on this power supply, I know because I've looked at it before, that opto isolator turning on turns the power supply on to this chip. The thing then fires up and starts giving all the output voltages. The second opto isolator is also coming from here, and this is your feedback, FB, feedback. This is monitoring all the voltage rails, 12 volt, 5 volt, 3.3 volt. And depending on the voltage here, it sends a feedback signal through this opto-isolator, again hot ground, into this chip, feedback. And that's how it controls the voltage rails. So that's basically how this works. There's one more opto-isolator here. This one is, again, this is safety ground on this side. This is monitoring the 5 volt standby, not directly, there's a bit of circuitry involved. A little reference TL431, but basically hot ground goes into your 5 volt standby. Oops, my pen's not working very well. There we go. Feedback 5 volt standby. So that's how this circuit basically works. The main difference is that the pulse width modulator is on the high voltage side. So again, it's separated, like the first one, via this transformer, via these opto-isolators, via this transformer, via these opto-isolators. That is your isolation from safety ground to hot ground, and it's important you understand that. Okay. Seeing as I've just done that, let's just go back to the first design we looked at. So, meter asking to shut down. This one, the isolation is via this transformer, okay, via these windings, this transformer, and then it's by the standby power supply, and via the opto-isolator. So again, you can see that the two halves of the circuit are completely isolated from each other physically and electrically. Let's have a look at the standby power supply in a little bit more detail. This is particularly for the type where it has an IC driving the 5 volt standby, not the little discrete circuit I showed you with the capacitors and transistors that makes a self-oscillating circuit. So in the ones where you have a driver IC, this obviously needs to get power from somewhere. And the way it usually works is this. It connects to hot ground, it's on the high voltage side of the circuit, and it'll have an input pin, VCC, a power input. You'll have a switch output, and this will go to MOSFET, or sometimes it's integrated in here, but it will often go to a MOSFET, just to draw the thing, rather than the transistor. Okay, let me draw it. Gate to hot ground, and the top end of the MOSFET will go to the transformer, primary, and then, as we said before, on the secondary you'll often have two windings, one of them supplying 5 volts and the other one around 16 to 24 volts, obviously with the associated rectifier diodes and capacitors on here. Now this top of this transformer, this is connecting effectively to your large capacitor, one or two of them on the input, to ground. Okay, and this is your bridge rectifier. So this is your positive supply, 270 volts DC, 380 volts DC, depending on if it has PFC. Now the way this chip powers up is actually really quite interesting. So normally from the VCC pin you will have one or more high value resistors connecting to here. There may, for example, be two of them in series, and each one is 1 mega ohm, giving you 2 mega ohms in series. And that is what powers up this chip, but only initially. So from this chip, we have here capacitor, hot ground. And the idea is that when you first switch on, these high value resistors charge this capacitor. And when the voltage on this VCC reaches a sufficient level, it switches on and starts driving the transformer. But this input has something called hysteresis. think it's spelled that way, you know, hysteresis. Somebody's going to tell me I spelled it wrong. So the way the hysteresis works is, when the voltage on here reaches a typical value, let's say 16 volts, this switch is on. Okay. Once this switch is on, this is now drawing power, so it starts to discharge this capacitor. And the way this circuit is designed is these resistors cannot provide enough current to keep this capacitor charged sufficiently to keep this running. So when this starts running and drawing a small amount of current, the capacitor starts to discharge. And the way this hysteresis works is the voltage here drops, but this doesn't turn off until it reaches a lower threshold voltage. Let's say 10 volts. It could be something different, but it'll be similar. So when the voltage here is high enough to switch on, this switch is on, starts running, yeah? And this starts to drain, and after a short period of time, maybe a second, this will drain and this will switch back off again because the voltage comes down to 10. Once it comes off, it won't turn back on until it reaches 16. So the voltage here, basically, I'll draw it where you can see it. The voltage here on VCC will effectively charge up to 16 volts. Yeah, the chip will switch on, so it'll discharge maybe down to 10 volts. This is 16 volts. And then once this switch is off, it'll charge up again to 16 volts, switch on, discharge again, and so on. And this is what you have here. Now, obviously, we need to keep this running. So what we actually have, in fact, is we have another secondary winding on this transformer. This secondary winding is connected from, I'll draw it in here, so it's on the same transformer. There's the secondary winding. This end again goes to hot ground. Okay. And this end now has a diode which charges another capacitor, a capacitor here, connecting to hot ground. Okay. This capacitor charges up, so once this power supply starts running, this secondary induces voltage, or rather supplies voltage to this diode and charges the capacitor. What you normally find then is you've got a resistor, another capacitor to ground again, hot ground, and also a Zener diode. Sorry, I've drawn the Zener. No, I've done it the right way up. I have a bad habit of doing that with Zeners. A Zener diode, okay? And then you will find that the output from here is connected to here, okay? VCC. Generally, by the way, there's also another diode in here. So that's how the circuit works. So now how this works is you switch on. These charge the capacitor. The capacitor reaches 16 volt and this switch is on. Once this is switched on, it's driving the MOSFET, driving the transformer, inducing the voltage into this secondary, rectified by the diode, charges this capacitor through the resistor, charges this capacitor. This Zener diode is just to maintain the voltage here at a set voltage. Once it reaches a certain amount, let's say 16 volts, this Zener diode will stop it going any higher than that. Okay, the 16 volts then supplies back to here. This diode is to isolate this point back from the mains because the diode only conducts one way. Now this supply can supply enough current to keep this chip running. So once this starts going and this is running, it keeps running. And that's the way it's designed. The idea of this is that if there's anything wrong on the standby, like a short circuit on the secondary or anything else, or this MOSFET's not running, or the chip's not running or driving it properly, that this will just switch on and off. Sometimes, by the way, depending on the type of chip, it switches on once, and when it comes back down to 10 volts, it switches off and stays off. So sometimes they will do this, charge up, come back down, and then just stay at 12, let's say 10 volts, yeah, 16 volts. This depends on the type of chip. This purely depends on the type of chip. So this type, once it's tried once, it just shuts down and you have to unplug the power and wait for this to discharge before it will start again. With this type, it'll just continually try to start. You find this in all sorts of small switch mode power supplies, and this, by the way, if you've ever wondered, when they make a chirping noise, yeah, you get this chirping every half a second or a second, it's this type of circuit that's causing that to happen. This circuit can quite often go wrong, by the way. So if these resistors go open circuit or high value, which can quite commonly happen, then they don't supply enough current to charge the capacitor. It never charges up to 16 and it won't switch on. If this capacitor goes leaky, so effectively it's leaking like a resistor here to ground, it'll form a voltage divider, and this will never reach enough voltage to switch it on. And the same can happen here if there's a problem with this diode or this capacitor. Quite commonly this capacitor has the one that fails. If one fails, there's not enough voltage coming out of here to keep this running. So that's what often happens with these. There's one other variant of this I'll just mention to you. So sometimes you'll find that the chip, this is basically a pulse width modulator, your standby control. Standby. Sometimes you'll find that this MOSFET is basically integrated inside the chip itself. So this MOSFET exists inside the chip itself to ground. Okay, this is your high voltage, high tension. This is your 270 volts coming in, and you'll sometimes find that the capacitor. So we have the capacitor here to ground. Okay, hot ground, hot ground. You'll find the capacitors here, and you'll find this circuit attached. So you'll find the winding from the secondary, this, coming back into here. But you won't find any high value resistors like these ones to the high voltage. And you'll think, well, how does it ever start up? And some of these chips, what you'll find is that those high value resistors effectively are inside the chip, connecting to there. So the only supply you see is this one coming from the secondary winding. If you keep that in mind, that will help you greatly when you're trying to repair ATX power supplies and they have a controller chip on the standby and it's not working or it's switching on and off. Here's the third power supply we're going to look at, and actually the last, because I don't have an example of the fourth type, which we'll talk about, but we'll still talk about it. So this is a more modern one. It's actually a 1500 watt power supply. It's faulty. I've now acquired this since the guy left the island and left it here. And I'll roughly explain how this one works. So this has 3 large capacitors, but they're all just wired in parallel there, yeah? So really it's effectively just having one large input capacitor. It has down under here, let me get the torch again. If you just see down here, yeah, there's that little circuit board down there. Although I haven't looked at it, I'm pretty sure that's the PFC controller. So this has PFC, active PFC, power factor correction. It has a large bridge rectifier with a heatsink on, and the PFC circuit is effectively down under here. Okay, these devices at this end, I'm just shining the torch in now. That's your power factor correction. You can see its power factor correction quite easily without looking. It has 1 MOSFET and 2 diodes probably in parallel. I haven't checked. It looks like they're in parallel. So we'll draw it and we'll put the two diodes in ours. But this is your PFC circuit. It then has the main switching transistors. Now, this is part of the fault because one of them's blown up, this one. Okay, but you see there's 2 transistors there, and there are 2 more transistors down the other side. It's very hard to see, but down under here, there's 2 more MOSFETs. And I'm fairly sure this is what's called a full bridge design, although I haven't tracked it out to prove it, but I'm fairly confident this is a full bridge design, which we'll look at. This transformer, this is your 5-volt standby, and very similar to that last one we looked at, it has a 7-pin chip. Is that just shining like here? So that 7-pin chip will be driving this transformer. The reason for the 7 pins, by the way, you can see they're like an 8-pin device, but 1 pin is missing. And the reason for that is because the pin after the gap, this has the high voltage on. Okay, so it's to stop it arcing across. That's why there's a gap. So that will be driving this transformer. This is your 5-volt standby. This will be probably a 5-volt regulator on 5-volt standby, some capacitors. Here, these are actually large chokes. Okay, one for each power rail. I think there's 2 chokes in each one. 1, 2, 3, 4. I have to say I'm not sure about this coil. I haven't really looked at that far on it at the moment. And this is your output capacitors all on here, and then your outputs. Now you might wonder where are the rectifier diodes, because we can't say the rectifier diodes, and that's because this doesn't actually have any as such. So if you look underneath, you'll see these large connections. These are your chokes I was just describing. 1, 2, 3, 4. Okay, there's like one there, one there, one there, and one there. And these are all MOSFETs, and these actually are your rectifier diodes effectively. And this uses something called synchronous rectification, which we'll look at on paper. This is the pulse width modulator for the main power supply, so it's on the low voltage side. We have 3 opto isolators here, probably doing what they were doing on the previous one. So one of them will be effectively controlling the output for the standby from this one, and then the other 2, one will be switching the pulse, sorry, one will be switching the PFC on, and the other one will be controlling it, I would think. Okay, again, I haven't looked at it exactly. And these big chips are effectively like opto isolators with MOSFET drivers built in. So there's 2 drivers in each one, and that drives the 4 MOSFETs. So let's have a look at this on paper. There is another circuit board down here as well, which comes onto here, which I think is all to do with the monitoring of the outputs. I think the fault on this, it probably has a short circuit output that caused the device to blow. Okay, let's have a look at this on paper so we can see what we have here. In a lot of ways, this is similar to the previous one we had. So we have the bridge rectifier. Same thing as before, plus, minus. This is your AC, live, neutral, coming in. And then from the bridge rectifier, we have, again, active PFC. The paper's not very level. Let's try and draw better than that. So we have the coil, the diode. It may or may not have the diode here. And this is going to the large capacitor. But in our case, there's actually 3 of these all wired and parallel like so. That makes this thing particularly dangerous, and if you want to go and watch one of my Christmas special videos with this power supply, you'll find out why. Okay, I'll link it from this video. How not to repair one of these. Okay, so that's what we basically have. Then we have 4 MOSFETs, and they are forming a full bridge, and I'll just basically draw that how it is simplified. So in a full bridge we have 4 MOSFETs. Well, they could be transistors again, bipolar, but I think this is using MOSFETs, so we'll draw MOSFETs. So we have 2 connected like so, and we have another 2 connected in the same way. So we have 2 lots of MOSFETs like this. And then the coil is connected from the junction of these 2 to the junction of these 2. So that's where your winding is connected. And then these go to the controller. In our case, we actually have 2 drivers, and these driver chips internally also have opto isolators built in them, and it's like a driver logic but opto-isolated. We have two of these, so we'll put them in here. Opto-isolated LED, and that's going to go to the other one. So that's what's driving it, yeah. These effectively like the opto drivers, you call them, yeah, opto drivers. This is then controlled by the pulse width modulator. Okay, and they're connected on here are your secondaries, but I'm just going to draw one secondary so I can sort of show you basically how this works. But you'll have secondaries for each of the voltage rails, okay, 3.3, 5, 12, but I'll just draw one of them. So that's effectively what we have here. Now this pulse width modulator again will need power, and this comes from, just as we had it before, your 5 volt standby. Okay, dodgy drawing, but there it is. Transformer. Yeah, this has that 7-pin chip on, 5 volt standby, and this is powered again from through some high value resistors from here. Okay, this is control. So this is your 5 volt standby. We better put a diode in there, haven't we? And we better put a capacitor on it. Okay, so 5 volt standby. This is your violet wire again, your purple wire. Okay, and once again we monitor this. This is looking very familiar, I'm sure, compared to the other ones now. This is your opto isolator, LED, photo transistor, and that's controlling the standby. So that's effectively monitoring. And again, there's a TL431 in here. It's a voltage reference. So there's a bit of circuitry involved. It doesn't just connect like that. This side is safety ground. Oh, I've made a mistake here. This side is hot ground. Okay, and that's how it's all connected. This is hot ground. This uses safety ground. Okay, so that's basically similar to what we had before. We now have the rectifier diodes, but we're not using rectifier diodes. So this is safety ground. Now let me just show you how these rectifier diodes actually work, or rather how these MOSFETs actually work. So the way this works, and first of all we'll just have to get rid of the ground because it's not quite like that. So we have 4 MOSFETs to form the rectifier. So we have one MOSFET here connecting to this end of the coil, and then we have another MOSFET here, and this is connecting to ground. Okay, and from the other end of the coil we have the same thing again. So we have one MOSFET going to ground, and we have another MOSFET up here, and that's going to the positive supply, which is here. Okay, so that's how it's actually connected. So we have 4 MOSFETs. Obviously all of them have gates on them, gate connections, and basically these are controlled by a synchronous rectification controller, which is built into this chip. So this is pulse width modulation, and it's also SRC, synchronous rectifier control. So this chip basically controls the gates to all of these MOSFETs, all 4 of them. And you may often find it's not just one MOSFET, but each one might be a number of MOSFETs in parallel. And basically this chip knows when these transistors are being switched on and off, and it also therefore knows when the positive and negative pulses are coming out of this transformer. And by switching the rectifiers in opposite pairs, it therefore generates your outputs, plus and ground, and your load capacitors are connected to here. So that's how your synchronous rectification works. The last thing we can just put on our diagram to complete this is we know this has active PFC, may have a resistor. connecting to there. So it has one or maybe two MOSFETs in parallel here. Quite possibly have two, could have one. And then this again, this is controlled by the PFC controller. Now on our board, I can see there's a little circuit board down in there, which I think is the PFC controller. So this is on the high voltage side. Okay, hot ground, and then that needs to be switched on and off. So again, from here we have the other two opto isolators. I mentioned there was two more opto isolators. So opto isolators in here to ground, safety ground, opto isolator in here to ground, safety ground, and these will be controlled from this chip again. So this is controlling both of these, and these via the transistors built into the opto isolator, hot ground, hot ground. These will be controlling this. One will be switching it on, either by switching the power supply to it on or by enabling it, depending on the chip, and the other one I think is controlling it. And I believe it kind of synchronizes the whole thing, so it's synchronizing this, this and this all together from this chip. But I don't know exactly, I haven't looked at the exact in and outs. But that effectively is a power supply with synchronous rectification. We have the same as before. We have the divide between the high voltage and low voltage side. So basically through here, and where did I put the other ones? Yes, through the transformer there. So again, we have no electrical connection from the high voltage hot ground side and the low voltage safety ground side. So that's the third type of ATX power supply you might come across. This one, someday I'll look at this again to repair it. I'll say I eventually acquired this. There's a couple of interesting things with it. It has these funny little windings around these chokes. Can you see them here? And I don't know if that's something to do with the sensing of the pulses of current, to do with the synchronous rectification. I haven't looked into what this actually is doing, or whether it's in somehow sensing to do with the power factor correction. I don't know exactly what they're doing, but they look like sensing windings to me. They seem to go over that way. But yeah, this one, if you guys are interested, I know you're going to be interested. We need to reverse engineer this. This went bang. There's a few components over here. I'll just show you. So you can see here, this is where something's gone bang. That's one of the large MOSFETs down here, which actually has completely blown the top off the device, as you can see. And we also have some components here which effectively blew the tops off these little transistors or MOSFETs. But because this is a full bridge, I think you can see quite clearly that we have 4 output devices on this. So we have 1, 2, 3, 4. And I would imagine that each of these 4 is effectively the same circuit over again, or 2 high side and 2 low side if you like. So I think it might be possible to reverse engineer all of this and therefore work out what's actually blown up. It's an interesting project. So yeah, what do you think, guys? Shall we try it? I will just tell you now how the 4th common design of ATX power supplies works, and this is in very modern ones. So what you tend to have is, and I don't have one to show you by the way, I'd like to get my hands on one of these faulty to repair sometime, but we basically have a similar thing to start off with. So we'll do it again. Bridge rectifier, AC, live neutral coming in. We have plus, minus. We have active PFC. So we put the MOSFET in down to ground. PFC. We have our diode, possibly this one. And we have our main capacitor or capacitors. This then basically drives a transformer in various ways. It could be a full bridge like we've just looped. I'll just put one MOSFET in for now. But this effectively drives a transformer. Let the ground come a bit lower. Which has pulse width modulation. Could be on either the high or low voltage side. PFC, I'm sure will be on the high voltage side. And then coming off here, we just have one coil. And this is one big 12 volt supply, or maybe more than 12 volts, maybe less, but it's one voltage supply. Rectifiers could be synchronous, like we were just looking at, maybe. Safety ground. And this then basically drives a load of buck regulators. Okay? These are buck regulators, like you get in the VRM, yeah? Look. And each one of these are all powered from here. Yeah, they're all connected to safety ground. And each one of these is a voltage rail. And maybe like 12 volts, 12 volts 1, 12 volts 2. So that's for like your ATX, for your connection. These are for your various, you know, the 8-way, the 6-ways. And you may have a number of different buck controllers on each voltage rail. 12 volts 3, and then we'll have the same 5 volts, and we'll have 3.3 volts. So we have something like that, yeah? 5 volts, 3.3 volts. We're still going to have some sort of standby supply. Standby driving a transformer. My drawing's getting very messy because I've been drawing for too long now. Okay, hot ground, safety ground, 5 volt standby, capacitors to ground, and this will be driving, or rather supplying power to this. So there'll be some sort of controller driving each buck regulator. Again, this is your purple wire or your violet wire. You'll have the green wire coming back in, which effectively switches all these on. So that's the other type. And I don't have one to show you, but you will, if you're working on modern ATX power supplies, find this design. Now let's look at the faulty power supply. So we know a short circuit. And I measured the short circuit across the bridge rectifier, which is here, this device. You can see, if we look down the side, that the middle 2 pins are AC. It's actually marked on the bridge rectifier. So we have AC and AC coming in, and we have plus and minus DC. And we're going across the plus and minus DC, which is the outside end, and this is where we can see the short. Yep, short circuit. That short circuit is basically across the capacitors. So the most likely place that's going to be is in the main switching transistors, which we were just looking at on the diagrams. In fact, I'll just show you again. Here is the diagram I made of this type of power supply. And we have a short circuit between the positive and negative of the bridge rectifier here to here. Ours doesn't have this PFC, so this positive, the bridge rectifier, connects directly to the capacitors. So if you look at this diagram, there's 3 places really that the short can be, because this doesn't exist. This is not on our circuit. So one possibility is that both of these capacitors are short circuit. Although that is within the realms of possibility just about, it's not very likely. And I doubt that's actually going to be where the problem is. It's much more likely to be in one of 2 other places. One is that both of these transistors are short circuit. So effectively the power is running down through here. Yeah, and that is quite likely. The other one, it is likely, but it may look strange on this diagram, we have on this diagram, I kind of drew it back to front here, but we have the switching transistor in the standby supply and the standby transformer, and this is actually connected between the positive and the negative of the bridge rectifier, albeit it's connected actually the other way around. I actually drew it back to front, but that also could be short circuit, and if that's short circuit, again through the primary transformer we have a short across here. So that's the two most likely cases. If we look on our board, you can see the two main switching transistors are here, and the one for the standby is there. So they're all on the same heatsink. So to remove this, I'm going to have to unsolder them all anyway. I can't easily get in here with a screwdriver, for instance, to like this one I can, but the other two I can't, to just remove the transistor. So the easy way to do this is remove the entire heatsink, including the transistors as well. And we can see that one of the main switching transistors here, 1, 2, 3, okay, and the other one is here, 1, 2, 3, and then the standby supply here is again 1, 2, 3. Also, there's a metal, there's probably two actually, metal support for the heatsink that's soldered on here, and I suspect there's one soldered on here as well. So effectively we have to desolder those 9 connections, then we can remove the whole heatsink, and once we've done that, with the transistor still mounted on here, we can test to see if we have some short circuits. The easiest way to do this is to add some leaded solder to all the points which we need to desolder. That will help to lower the melting point, because this is almost certainly lead-free solder. And again, for the two posts mounting the heatsink, I'm going to try then to use a vacuum desoldering tool to remove it. You could use a braid. I'm not going to add flux if I can avoid it. The reason being because the flux has a habit of clogging up the vacuum desoldering tool. So it's better if you're going to use that method to not add flux if you can avoid doing so. If you're going to be using solder braid, you might as well put flux on. So we've got 3 there. We've got 3 here. Okay, and we have the 3 pins of the standby transistor or MOSFET here. 1, 2, 3, and then I'm sure this is one end of the actual heatsink. Solder on that one, and this is the other end, the other mounting post on the heatsink. So I've added some leaded solder to all those points. Now let's get the vacuum desoldering tool. I'll just give this a clean. It sounds like it's slightly clogged up, so I'll just clean this before we use it. Let's see if it actually has got a blockage in it. No, it's clean, it's clean. Okay. Now I can hear it sucking air much better, so it obviously was slightly clogged. So we have the devices to unsolder. So we can get on. These large ones, where the legs are too large to effectively go up the nozzle, you might find it's easier to just come in with the solder from one side of the pin with the soldering iron and with the vacuum tool and do it like that. You may find you get a better result, and you may also have to do them, you know, add a bit more leaded solder and go again. Yeah, so we can do it this way. This is working quite well. So that's 3 there. Again, let's get some heat into it. As you can see, this is quite a nice technique. You can do the same thing with the vacuum tool plus hot air as well. And these won't be so bad because these are small pins on this MOSFET. This is just going, no problem. People ask about this. This is a Pros kit, SS331H, I believe. I'll put it in the comments. Not sorry, in the comments. I'll put it in the video description. Okay. That's getting some heat into there, and this is the other end of the heatsink. And hopefully that is desoldered. If you're using one of these tools, every time you finish using it, you should again run the needle through it just to make sure it's not clogged. You see that's got a little bit clogged there. If you do this now before it cools down, it's much easier. If we take a pair of needle nose pliers out, you see it's pushed it past it. Yeah. If you do that later, once it's cooled down, it's much more difficult. Let's see if this is now ready to remove. So I can rock it backwards and forwards. I'm just looking at the actual pins of the devices to see if they're moving freely. I'd say that this one or two are kind of like held on by residues of solder. So let's just see if we can just free them up as this one. I think maybe we'll push one of these two legs towards me. That one. That one. That one. They seem to be free now. So you don't, put too much pressure on this. Just do it nice and steady. Try and free all the things up. Okay. Yeah, it's come out at one end now, and it's coming out. Do this nice and gently, you won't take any pads with it. Well, it's not too bad on a single-sided board like this, to be honest. I can feel something, yeah, it's got it. So there you see, came out nice and gently, and we have our devices so we can test them all. Let's see if we have a short circuit somewhere on here. Just clean the dust and fluff off it. These two are marked 3DD13009. I can look at the data sheet, and this one is C5027. Maybe a transistor. These might be MOSFETs. We can test. We can use the component analyzer. That's the easy way. We can look up the data sheet. So let's just try test these with a multimeter using diode mode to see if we can identify what we have. So we'll go to diode range, and let's have a look to see what we've got. If this is a transistor, it's probably base collector emitter, and if it's a FET, it's probably gate source drain or gate drain source. So we have nothing there. We want diode mode. Or just, one of the meter leads fell out. Just typical. Okay. Test the equipment. Now let's have a look. If it's NPN, there'd be base. We should get a diode junction. Diode junction. Diode junction. So that looks okay. And this is checking like a bipolar transistor, base collector emitter. You can sometimes tell which is the collector emitter, apart from the arrangement of the pins if you know them, by the voltage. That's 0.570. That's 0.598. The one with the slightly higher voltage is normally the base emitter junction. Okay. These are possibly MOSFETs, possibly transistors, or possibly just short circuit. That reads short. That reads short. So these devices are where the short circuit is. Okay. Completely short. So we need to have a look to see what these actually are and if we have something suitable to fit in its place. So let's try and find the data sheet. This is alltransistor.com. It's a very good place to look for data sheets for transistors. You'll find the data sheets in lots of sites, but this will also help you to find an equivalent if you don't have an original one, if that is possible. So it's a silicon NPN transistor. We can see it's 700 volts, 12 amp, probably have a wattage somewhere. And this is the actual data sheet. We can actually have a look. Let's get rid of the advert, go away. So this is the data sheet. It's basically showed us what we've just read. These adverts do annoy me. Go away. Oh, okay. I'm sure they annoy you as well. But it's even more annoying when it's somebody else's adverts, yeah? Okay, so we have it. 700 volts, 12 amp. And it was, I'm just trying to find out the wattage of this actually. Oh, 2 watt, quite a low wattage transistor actually. But there's the main values of it. I don't have these in stock. I can get them quite cheap from AliExpress. Maybe €2 or something for a pair, and I might end up doing that. But let's see if we can actually find an equivalent in something I maybe do have that would actually work in this case. Notice it says the package is TO220, and actually ours are not. Ours are not actually matching the package of this. You can see on the data sheet the actual the picture of it. Yeah, that's interesting. That was same part number but a different type of package. They're much larger. I'll show you again in a minute. Equivalence, and there's a thing somewhere in here. Equivalent substitute. Let's have a look, see what we can find. No, you know, I thought that would just give us the equivalent. Oh, there we are. Cross-reference to the one that I've just found. So here's the number of different parts. Let me see if I've got anything that is on this list that I can actually put in here. I don't have any equivalents in stock. I can get 5 of these for €2.86 plus 150 shipping, so 3.86, about €4.30. Probably won't be here till middle of June, but I can get 5 of these, which actually seems to be quite a useful part to keep in stock because I have nothing like this. So I'm happy to buy a few of those. So I'll put them in the cart, and I can order those. But in the meantime, let's have another look at our PCB and see if we can see any other problems that might have been caused by these short circuit transistors. This is where we've taken the transistors from. Because they were short circuit, we can be sure, in fact we can just look at it, that the fuse is blown. It's kind of all burnt out in there, so we know the fuse is gone. But that's not a problem to replace the fuse. Has this caused any other damage that we should check for? Well, it's possible. This transformer drives the bases of these transistors, so this isolates this circuit from the other side, which is the transistor over here and the chip. So it's extremely unlikely that any damage has gone back as far as there. But if we look down here, we have a few components. This transistor is actually involved in the standby supply. If you look at this board, you might have wondered this, where's the controller chip for the standby supply? Well, actually there isn't one. This transistor, the transistor in the opto-isolator, and the actual output transistor, together with these two capacitors and a few components around here, this forms an oscillator circuit. So this is a self-oscillating circuit, and this photo transistor, which is connected in here, affects the frequency of it. So basically that's how it works. If it's not affecting the frequency, it's affecting the duty cycle of it. So that basically is your oscillator that drives this transformer in the standby supply. The other components around here are involved with the drive to these. I know these two diodes will be, and these two capacitors will be, and there's a few other resistors and diodes around here as well. So let's have a look in this area to see if there's anything else we can see that we need to replace. The most likely components to be damaged are the diodes. So we'll check all these diodes. This is one of them. Shouldn't conduct this way, and it should conduct the other way. That reads good. Same with this one. Should conduct this way, and that reads good. You can see a voltage drop. There's two small diodes down here which are involved in the base drive. That's this one, and that reads okay. The other way should just read open. Yeah, we get some reading, but that's because there's other things like resistors in here. But it's definitely got a good diode junction. This is the other one. Yeah, and we can go the other way across it. Yeah, it just reads like effectively something, but it's because the resistor there. Let's go to resistance range now. Let's have a look at the resistors. I've gone too far. Go around again. Resistance, okay. Let's have a look at the resistors down here. So what can we see? Well, there's a couple of 470k resistors. If it reads its value or less in circuit is generally good because resistors don't fail by going low. If it reads higher than its rated value, it's generally faulty because resistors do fail by going open or high. So they look okay. This lot here is going to be involved with the standby supply. We have another one here. Let's have a look at it. Is it what's it reading? Get connection noise. 2.7. Yeah, I think you can see that's a 2.7k. Red, violet, red. This one looks a low value resistor. 10 divided by 0.1. It's a 1 ohm resistor, I think. Yeah, 1.1 ohm. That reads close enough. 1 ohm it's reading. That's okay. Looks like another 2.7k. Looks like another. This one's, yeah, the low value again, same as that one. 1 ohm resistor, looks okay. Couple more in here. What's this one reading? 27k. Let's look at it. Yeah. Red, purple, red. 27k. Yes, they all look okay. We have a power resistor here, which I think we just need to check this one. $100 ohm, is it? Yeah, 100 ohm. Yeah, brown, black, 100 ohms. So all those checking okay. This capacitor is the one in the diagram. I'll just show it to you. It's this capacitor here. If that went short, it could quite likely expect it to blow these. I wouldn't be surprised. We can check this. Normally if these fail, they go low capacitance and the thing won't work or won't work properly, or they go open circuit and it won't work at all. So we can have a look at the capacitor. I'm just looking to see if it's shorted at the moment. Let's have a quick look at this. Yeah, it's not short circuit, it's a high resistance, well into the kilo ohms. And because we've disconnected the MOSFETs, we've actually effectively disconnected one end of it, so we should be able to read the capacitance of this in the circuit as well. So let's have a look. I haven't looked at the value. They're normally something like 220 or 470 nanofarad, something like that, maybe 1 microfarad. Let's have a look. Okay, I'm not reading anything there, so I'll just give it one more go. So I might be inclined just to remove this and to have a look to see what it's actually reading. Yeah, I'm not seeing any reading there at all. Oh, no, I am. It just takes a while. So it's actually higher than I thought. It's 2.7 microfarads. Let's have a look to see what it actually says on the capacitor. It's saying it's 2.2 microfarads there. 225, yeah. Yeah, 2.2. So that's reading about right. The thing I'm more inclined to check, and I say you always need to check, is these two small capacitors. These again are involved in the base drive circuit, and a failure here can blow the transistors. So let's remove these two and just check if they're okay. I might be able to measure in circuit actually because the transistors are removed, so we can just give that a go first. If not, we can just take them out and see how they're reading. Let's have a look. One of them is mounted here. Well, there's, see if it actually reads on the capacitance meter. Yeah, it can't read it in circuit. That doesn't particularly surprise me. So I'm going to take that one out and the other one as well. So let's take those out to make sure they're okay. These are the two capacitors. They're 2.2 microfarad 50 volt. I don't think these are low ESR capacitors. Well, they could be. I mean, there's some high frequency signals in this area. But we can have a look. So this is reading 2.36. That looks good to me. And this one, let's see what she's reading. Okay, onto it. A little bit fiddly, but I'm sure I will get onto it. Negative. Yeah, same sort of value. I'll check the ESR anyway. Let's just see. I mean, for such a small capacitor, the ESR would be fairly high normally. Okay, so we can just have a look at these. But I'm thinking these are probably okay. Let's have a look at this one. Yeah, 3.6, good if it's less than 22 microfarads. It probably is okay. Somebody on the comments going to tell me that isn't okay, so when he tells me it isn't okay, I'll change it anyway. But I don't think that's too far out of the way for a capacitor of this value. We can try one from my stash of salvage bits. Yeah, it's about the same, that's that one. Go on, let's try one of my salvage ones as well, just out of interest. I have one here, same value, 2.2 microfarad, 50 volt. Let's see what this one's doing. And if this is very similar, I think those two are actually okay. So it's dropped it, let's just go again. Okay, measure it. Okay, no, it reads lower. So I could replace those. I'll just find another one like this, and yeah, we'll put these in. Okay, I've replaced those capacitors. Now let's have a look on the secondary, the low voltage side of this. So straight away we can see here we have a bulged capacitor. This capacitor's gone. It's a 2200 microfarads, whichever volts, probably 16. I can't just quite see, but I'm sure I've got those in stock, so that's not a problem. That's gone. If there's any the same as that one in value and make, they've probably gone as well, so we may as well change. I think that looks like the same type as that one, so we can probably change those. But there's another reason why these transistors might have blown. I don't think that capacitor is it. The other reason is that there's a short circuit on one of the outputs, so this is well worth checking. The easiest way is just to check actually where the wires come onto here. So let's have a look to see if we have any shorts here. I'll use the ohms range rather than the continuity range actually, so I expect to see some resistance here. So we need to go, it's probably easier from underneath. So this is where all the black wires come to. This is where all the yellow wires come to. This is the 12 volts. And that's fine. Yeah, there's no short there. This is where the red wires come to. So this is the 5 volts. Again, there's no short there. There's a blue one. This will be a minus supply. And actually, you know, no current draw from that. It's in well into the kilo ohms. And then we have the orange, which is the 3.3, which are here. So this I'm expecting to read a lower resistance. Normally there's a load on it, like a resistor, a power resistor, 37 ohms. That's fine. So we don't have any shorts on the output, and we can confidently say that we don't have any short circuit diodes here. And on this heatsink, there's one large one and two small ones. Although these are 3 pins, these will be diodes. Can you see the symbol on this one? Probably, yeah, in the middle. You'll see like 2 diodes with the cathodes, like common cathodes together here. And this will be the same. And this one, just see it. Yeah, down in the corner there, same thing, 2 diodes, common cathodes. So we can test these. We can probably do it from this side actually. Let's go on to diode mode. But because there's no shorts on the output, I honestly don't believe there's going to be shorts here. So let's have a look. So the common cathode. So the positive on the anode, which is over here. Yeah, we can go to the middle leg and we should see a diode junction. Be a Schottky diode, so it'll be quite low. That's reading particularly low actually. That's actually a bit unusually low. Might be worth just checking that one. And what's it reading on the other leg? The same. That's a little bit unusual. You'd expect them to read about 1.3, 0.13, 0.15. What's this one reading? Yeah, something like that, 0.23. That's like a good Schottky diode. Let's go the other way. Yeah. And then we can do the same with the middle one, which is hard to get to the pins. So I think with this one we'll actually do it from the other side of the board. We can see one of them's here. Where I've got my finger on it. Yeah, the one we were interested in is actually here. So we can just check it here. So common cathode. So that one reads quite well as well. Okay. These might just be the type of diode, but there's no harm in just removing this. I mean, it was easy enough to remove the other heatsink, so when we get this far, we might as well just take this out and just check to make sure these are actually all okay. I've removed the heatsink with the devices exactly the same way I did for the power transistors, and you can see now the two small devices are actually different. Yeah, they're not the same as each other. They're both dual diodes, common cathode, but they're not the same device. So that may well explain why we have a different reading on them. This one, the large one, obviously is a different device. So let's have a look now to see on the meter and diode mode what we can actually see. I'll just move the things so it's not reflecting into the camera off the overhead lighting. So okay, let's see. We have 0.271, 0.271, 0.135, 0.150. Oh, that's a little bit strange. Oh, it's the same both sides. 135, 135. So these actually read okay. 138, 139. They read okay. I think it's the other reading is just due to other components in the circuit, capacitors and such like, which will take some time to charge up. While we have this here, let's just try the component analyzer as well, and we might as well just check the this device, which looks okay on the meter. But let's have a quick look. This is the component analyzer, the Peak, which I use. I also have one of the cheap ones, but I find this more convenient to use. On this one, we figured out with the meter that this was the emitter because we had the slightly higher voltage drop between base emitter than we did between base and collector. So let's have a look. Let's put the green wire on here and let's see if it tells us that the green wire is in fact the emitter, to show that that actually gave us the correct result. So we put that on there, hit test, and let's just see what it thinks. Yes, it's a silicon transistor, and the green wire is the emitter, so that just proves what I was showing you with the multimeter, that you can often tell which the emitter is. Okay, that was okay. The other two are short, we know that. These we can test on here. I mean, we know they're okay, but just for the sake of a few more watch minutes, let's just try them. So this should say something like diode matrix. Common cathode diode network, so it's happy with that. Oh, I think the button's stuck in and it's switched off. Let's do it again. Pin out for D1. Oh yeah, showing you. Yeah. So yeah, and the red is the actual cathode. So I'll get the other two. Put on this one. Okay. Test. Should say the same thing. Yeah. Common cathode diode network is happy with that. And let's go to the last one. Clip is just still a bit stuck. Okay. Move on. Let's try it. Hit the test button. Okay, and another one. So we know that all those are okay. Is there anything else we should check on this just before we put it on one side and wait for the transistors to arrive? And actually, yes, there is. Because of the nature of the fault here, which was a short circuit and the two main transistors driving the power supply, we really need to check everything before that. So, in particular, we know the fuse is blown. This thermistor, which is in series with the AC coming in, that could have gone open circuit. The easiest way to check is to see if we have continuity from the AC wires coming in to the actual AC connections on the bridge rectifier, which are these two. So probably the easiest way to do this is just to turn it upside down. So these are the two AC terminals on the bridge rectifier. The DC terminals are here. So it's these two. And what we need to check is whether we have a continuity from both of these coming back to where the mains comes in. One of them should probably just read continuity because the fuse is only in one of the leads. So let's have a look. This is where the blue wire is coming in. Is this going to one of these? Yeah, so that has continuity to there. That's the neutral wire. The live wire comes here, goes through the fuse. Now the fuse is open circuit, so we'll check from this side of the fuse. And it follows, so I can see it follows through here actually, and it should come to the other side of the bridge rectifier, which actually is here. Yeah. So we have continuity from there as well. We have continuity from both sides. So we know that all this circuitry in between is good. The other thing we should definitely check is whether the bridge rectifier is good. Now let me show you how to test a bridge rectifier. I might as well do it from this side where you can see the diodes or the marking. So this is the positive terminal. So with a good bridge rectifier on diode mode, if we go from one of the AC in and to the positive, we should read a diode junction. You can see we're actually reading a short. So this is actually short circuit. Yeah, let's go from the other side. Yeah, it's short circuit on one leg. So we actually have here a faulty bridge rectifier as well. So one of the two AC diodes coming to here, positive is faulty. What's all the negative ones? So with the negative we go the opposite way. We put the red lead to the negative terminal and the black one's coming in. That's okay. That's short. Again, we have a short there. So this bridge rectifier is actually reading faulty. If we go across the two main terminals, the short is now gone. That's the shorted transistors. That short is now gone. To compare this, you need to have a look at the good bridge rectifier. So let me actually show you how to test a bridge rectifier. Here we have a bridge rectifier. I think this is a good one. It's a salvage one. So let's have a look again. So with the red lead to the AC, both of these terminals should have a diode junction to here, the positive. So let's have a look. That's a diode junction. That's a diode junction. That's a good one. On our 41, one of them is showing short. And then with the black lead, the negative coming in, this is a way to think of it. You've got the negative coming in. So with the negative coming in, both should show diode junction to negative. So we put the red lead over here, and this is the negative coming in. Okay, that's a good one compared to the one I've just tested in circuit, which had two short circuit diodes. Out of interest, with a bridge rectifier, if you test from the positive to negative with the red lead to positive, it should just read open circuit. Okay, but if you connect the other way with the red lead to negative, you'll see two diodes in series normally. Yeah, there, 1003, that's 2 times 0.5, that's two diodes in series. That is normal for a good bridge rectifier. Let's take the faulty one off the circuit board and let's just compare it out of circuit as well. Here's the bad one. I just decided to cut the legs off actually, so I can then easily remove the 4 pins that are going through the board because I know it's faulty. So again, with the positive coming in, the red lead, we should have a connection from both of the AC terminals to positive. So that one's a short circuit one, that one is a diode. Okay, and then with the negative coming in, the black lead, we should have a connection from both to negative. That's a good one, and that's short. So we see two short circuit diodes. We can go with the red to positive and we should see nothing. That happens. And then with the red to the negative, we should see two diodes in series reading about 1.0, which it does. No, it reads 0.5 because one of them is short. So we have there a faulty bridge rectifier as well. And this is because of the high surge current. Now you could replace this with another bridge rectifier. You could look up the current and voltage rating of this, but basically it'll be 400 volt or better, and however many amps the power supply is drawing. You could, if you wish, and this is where I just removed it from, you see there's 4 diodes marked on here. You can always replace a bridge rectifier with 4 individual diodes if you don't have a bridge, as long as they're a high enough voltage. In this case it's mains 220 volts, so 400 volt or more, and of a sufficient current rating, which you can work out from this part number. So you can always do that. And by the way, you can also replace 4 individual diodes with a bridge rectifier. Have we finished now? Well, I can think of at least one other thing that we should be checking in this sort of situation where we've had a very powerful surge of current running through it, which has obviously damaged a number of things, well, the bridge and the transistors anyway. It's just to check the transformer primaries, just to make sure they haven't got an open circuit. This won't tell you exactly if they're good, because it won't tell you if they have a shorted turn or such like, but it will certainly tell if it's open circuit. That one's okay. And this is the one on the drive circuit. And that's reading okay. So both the little drive, oh, and then my meter fell over. Captain Chaos strikes again. Okay, so both the main transformer primary and the secondary of the one that's driving the base circuit are okay, or at least they're not open circuit. I mean, they could be burned to have shorted turns, but it's not so likely. So after all those checks, I think we can say with certainty now this needs a fuse, a bridge rectifier and 2 transistors, and we have an extremely high probability of success if we replace those parts to find that we have a working ATX power supply. Okay guys, so that started as a ATX repair video, and kind of I went off on one and ended up with a dissertation on ATX power supply design, safety, repair techniques and servicing. I hope you enjoyed that video if you made it this far, and as always I'd like to hear your comments in the comments below. Let me know what you think. Let me know, because I'm sure there's things I missed, maybe important facts that I missed. So yeah guys, you know, this is a community. Just get your comments. If they're criticisms, that's fine. You know, I'd prefer you make them constructive criticisms. You know, tell me where I'm wrong, that's fine, and I'll hold my hands up. Yeah, if I'm wrong, I'm wrong. If I'm right, I'll tell you why I think I'm right. Yeah, and I might just say yeah, well, yes but no but. Okay guys, that's the end of that. I will see you all soon on another Learning Electronics Repair video. Ciao for now.